Alright, so far we've discussed the gravitational energy an object can have, and that sometimes it's called the potential energy or the gravitational potential energy. And it's due to a gravitational field. And yesterday we discussed how there can be conservative forces and non-conservative forces, and field forces are always conservative. So beyond the gravitational field, there's an electric field and there is a magnetic field, and any work they do is conservative. Okay, so let's just take a case where we have a block and it's in the gravitational field, and here is the ground. So this is where y is equal to 0. And neglecting any air resistance, if this block is just here, we're just looking at it all by itself, it has one force on it, a gravitational force, which would be equal to its mass times the gravitational field constant. And if it goes from this position here, let's call this H, to the ground where the position is 0, then we could calculate the change in gravitational potential energy as the final gravitational potential energy minus the initial gravitational potential energy. So far so good? Okay. Now what about the work done by the gravitational force? So work is done by a force that's applied when it's parallel to the displacement. So what force is the gravitational field applying?
Downwards.
It is downwards. But what do we call that force? The force due to gravity, and we can calculate it by m times g. And then remember, if work is force times distance, then what would the distance be here? H. So our change in gravitational energy was negative mgh, and our work done by the gravitational field was equal to mgh. What kind of relationship then could I write between the change in gravitational potential energy and the work done by the gravitational? The magnitudes are equal. And why is it just the magnitudes that are equal?
Because work doesn't have
So would work done by the gravitational field be equivalent to the negative change in gravitational potential energy? Alright, so let's go back to the simplest definition for work. Alright, so if I have a graph of force and distance, and that force is constant over a particular distance d, then the work done by that constant force would be the magnitude of the force, that it's parallel to the distance, times the distance. Force parallel times the distance. So graphically, what would the work be equivalent to? The area under the curve would be the work. Alright, so what is area also known as?
Times width.
A fancy calculus way, it can also be the integral of the force with respect to position. So there was a force that we studied, the spring force, and the magnitude of the spring force is k times x. So that means that if I graph this function, force versus change in position, what would that look like?
Sloping downwards.
It would be like this. like this. Wouldn't that be the function? F equals kx. Positive slope, and then x is the variable. Okay? So using the idea that work is the area under function, this would be x. How would you find the area then graphically? 1/2 base times height. Oh, how am I going to find the height? What is this force up here going to be equal to? Kx. Very good. So multiply that by k times x, and you get 1/2 kx squared, which is the work done in compressing the spring or stretching the spring, which is then also the energy stored in the spring. What if instead we were looking for the work done and we took the integral from 0 to x of the force function kx dx? So x is the integration variable, so we raise it to 1 power, plus 1 power, so it will be x to the 1 plus 1, and then we divide by the new power, and then we evaluate it from 0 to x. That looks like 1/2 kx squared.
Wow. Is the dx in the integral, is that just notation?
Yeah, it's in relation.
Yes. That means that I'm going to take an integral with respect to that x right there. If it was dt, then it would be, there's no t there, and so it would just be kxt.
Never forget it.
Okay, so in general then, if you have the change in, let me actually write it this way. If the work done by the gravitational field, which is conservative, is equal to the negative change in the potential energy or the gravitational energy of that conservative field, and work is the integral of the conservative force with respect to displacement, then I can find the change in the potential energy of that conservative field. So this works for electric fields as well. So that's why I'm just kind of lumping it all into one kind of equation here, okay? Now, most of the time, the E conservative notation in textbooks and even on the AP exam is a U. So you'll see this written as delta U. That's what the is also a way to write it.
Is there a reason to U? Or is that
It's just a symbol. Like we decided K would be the spring constant symbol. We decided M would be the symbol for mass. Energy stored is that U. We could make a general statement, and that is that any work done by any conservative field is equal to that negative change in energy of that conservative field, and that the change in energy, potential energy, stored energy of that conservative field would be equal to negative. So I'm just bringing the negative over to this side. The negative integral of the force of that conservative field dx. So things like friction, tension, a pushing force, those are all non-conservative. So if you name a force that's not due to the gravitational field or the electric field, then you have named a non-conservative force. Now, for the sake of making things interesting, sometimes we make up things and say, hey, for example, there is a conservative force of negative 2x plus 4. Okay, so we've got this force that is supposedly conservative, and it's varying with position. And then you could give me what is the change in the energy stored in that conservative field. And you don't always have to write CONS.
Isn't it like indefinite? So how would you what do you denote as yours?
From 0 to 2 meters. Negative 2x plus 4 dx. So then, oops, I need a negative sign out there, right? So it'll be negative, negative 2x squared over 2 plus 4x, evaluated from 0 to 2. Did I do that correctly? Okay. Which would look like what? X squared minus 4x from 0 to 2. Just a little simplification there. So then 4 minus 8 minus 0, and that would give you what? Negative 4? Negative 4 what? Joules. Because we're still looking at energy. So if I had a graph of the energy stored, so this conservative energy with respect to position x. And let's say it looks like this. Okay. From 0 to some later position x. Can you tell me, just qualitatively, not quantitatively, there's no numbers, qualitatively, what direction would the force, the conservative force, on this object be at this point right here? So if the change is equal to negative integral of f dx, could I write this as du is equal to negative integral of f dx? Or actually, let me take the derivative of both sides. There we go. I did something silly there. And so then the force would be negative du dx. So what's the direction of the force at this point right here? What does du dx mean?
Changing u over changing.
In terms of a graph, it is the slope. And so the slope of this line that passes through that little dot that I drew on there, that's a positive slope. So then what's the force? Negative. Okay. So the force would be equal to the negative slope. So far so good? Okay. So what if I have something like the energy stored with res-